In this video, we're going to be discussing the path of flow within a mechanical fuel injection pump, specifically the opposed plunger, otherwise known as the rotary or distributor pump. Now, before we dive into the pump itself, we need to understand where everything begins and the journey in which fuel embarks on. Everything begins at the fuel tank. The fuel tank is a reservoir that must hold sufficient enough fuel for continuous engine operation. From here, the tank allows returned fuel to settle and cool before being recycled through the system. Pressures in this tank are kept atmospheric, which is about 14.7 psi for ease of withdrawal. From there, the fuel is sucked into the system via a lift pump. However, before this, the fuel must pass through a primary filter first. So just imagine a filter right before the pump. Now in this first filter, we filter out particulates greater than 25 microns in size. Primary filters are often combined with a water separator, which is designed so that water collects at the bottom section where it can later be drained off. Now compared to water, which has a specific gravity of 1, diesel fuel has a specific gravity of approximately 0.85, making it lighter than water, and therefore water collects beneath the fuel. This then pushes the fuel towards a secondary filter at a working pressure of about 3 to 5 pounds per square inch. Once the fuel arrives at this filter, particles larger than 5 microns will be kept out of the rest of the system. Reason being, the injection pump consists of very close tolerances, about 1 to 3 microns. Abrasive materials such as dirt or water will wear out the pump, causing a reduction in output or even complete failure of the assembly. After passing through the secondary filter, our fuel now begins its journey through the distributor pump, which is going to be this side of the diagram. Fuel flows in through the inlet by means of the vane type transfer pump, but not without passing through one final filtration element, the inlet screen. This final stage of filtration has holes as small as 2 to 3 thousandths of an inch, being the system's last line of defense. So, fuel comes in through the inlet, past the screen, and then the transfer pump, which is driven by the rotor of the injection pump, sucks fuel into the assembly. This marks the entrance to the fuel pressure regulator, which is going to be this guy right here. So the regulator acts as a sort of relief valve. But instead of sending excess fuel back into the tank, it cycles it back into the inlet side of the pump. Fuel output from this transfer pump pushes on a regulating piston against spring tension. This controls a transfer pump pressure to about 26 psi during cranking and 40 psi at idle. This is because as rotor speed increases, so does the volume and pressure. And as RPMs increase, the pump flow does too. And therefore, the regulating piston, once pushed sufficiently against the spring, it uncovers the regulating slot, letting excess fuel back into the low pressure side of the inlet. The maximum pressure of the regulating valve sits between 90 and 120 psi at high idle, depending on the manufacturer. So, fuel flowing past the transfer pump is now on its way to the metering valve, as well as the timing advance mechanism. In addition, some of the fuel works to fill the pump housing. A return line flowing from the pump housing regulates the housing pressure using a check valve set to 4 pounds per square inch. This is the metering valve. It controls the volume of fuel being delivered to the rotor fuel inlet and pumping chamber. It is also connected to the governor and throttle by means of a mechanical linkage or an electric solenoid. Depending on the position of the metering valve, it can increase or decrease the quantity of fuel being delivered. Fuel can also be shut off when rotated to a position that completely blocks off fuel delivery. The main pumping element of the opposed plunger injection pump revolves within a stationary cam ring. The number of lobes is usually the same as the number of cylinders in the engine. This cam ring, for example, has 8 lobes, suggesting it's part of an 8-cylinder engine. These rollers are retained by a roller shoe, and a small leaf spring secures the shoes onto the rotor. As the drive shaft drives the rotor, this charging port lines up with the fuel inlet, allowing low pressure fuel from the metering valve to enter the pumping chamber. The plungers are then forced apart as the rollers move into the cavity between each of the cam lobes. The distance that the plungers move apart depends on the volume of fuel that's being metered into the pumping chamber. And the amount of fuel that's metered into the pumping chamber also depends on the metering valve's position, the transfer pressure, and the amount of time that the inlet and charging ports are lined. This entire dance represents the charging or the loading action of the pump. When discharging or injecting the fuel, the rollers riding on the camring contact the lobes and the plungers are mechanically forced towards each other. The fuel inlet and charging ports are no longer aligned, but instead, the outlet ports begin alignment with the charging ports. This action squeezes out the fuel at high pressures, forcing it out to the high pressure fuel lines made up of equal length heavy wall seamless steel tubing. The rotor continues to revolve in the hydraulic head, continuing the sequence of charge and discharge. One single revolution delivers fuel to all the cylinders in the firing order. Fuel takes a certain amount of time to ignite, regardless of RPM. Therefore, we need a system in place to adjust the timing to compensate. The speed advance mechanism advances or allows the fuel to inject earlier, based on an increase in transfer pressure. As RPM increases, the transfer pressure increases. The timing advance mechanism comprises of a camron, an advance pin, an advance piston, and a spring. The pin which sits in between the piston and spring is mounted together with the camron. If the pin moves, so does the camron. At lower pressures, the spring is always pushing on the pin to retard the timing. As engine speed increases, transfer pressure increases, which then acts on the piston, pushing the camring in the opposite direction against spring tension. By doing so, the camring is pushed in a direction that opposes normal pump rotation, thus allowing the plungers to contact the cam lobes earlier. The timing is advanced. Here it is again. Higher transfer pressures due to increased engine speeds push on this pin against the tension of the spring. In doing so, the timing mark on this camering can be seen moving in the opposite direction of pump rotation. Since the injection pump travels at half the speed of the crankshaft, the amount of timing advance at the injection pump doubles at the crankshaft. For example, if we advance the timing at the pump about 2 degrees, the timing advance at the crankshaft would be seen at 4 degrees. After being injected, some of the remaining fuel left in the injector is returned to tank. This return line may be fitted with a restriction or orifice that aids in reducing the pressures, removing all air bubbles, and ensures smooth engine operation. That leaves us with the governor. The main purpose of the governor in this situation is to regulate RPM and power output. On our opposed plunger pump, the governor is located right here, on the opposite side of the pump's inlet. As we can see, the governor is mechanically linked to the metering valve. This specific governor consists of multiple flyweights. As the engine speed increases, these flyweights naturally want to move out due to the centrifugal force imposed. As the flyweights move out, they pivot and push the thrust sleeve against a spring force. This thrust sleeve is linked to the metering valve, which then actuates the inlet metering valve, adjusting the volume of fuel being supplied. Although this diagram does not accurately represent our specific injection pump, it gives us a better visual representation of how the governor works. As engine speed increases, the drive shaft, which is joined together with the flyweight assembly, spins faster. This increase in centrifugal force pivots the flyweights outwards, pushing on the thrust sleeve, which is mechanically linked to the metering valve. Just imagine this is the metering valve for now. As engine speed decreases, the spring wins the battle and returns the flyweights back to their original position, as centrifugal force no longer overpowers the spring tension. Higher engine speeds would incline for a lesser fuel situation to prevent overspeeding, while lower engine RPMs would incline for more fuel from the metering valve to maintain a specific RPM and prevent stalling. In our specific injection pump, the throttle is mechanically linked to the metering valve, which holds the spring tension that the governor fights against. Same concept, the operator depresses the accelerator, moving the metering valve into an increased fuel position, thus increasing your engine speed. Due to the speed increase, centrifugal force moves the flyweights outwards. A balance is achieved by the counteracting components, and therefore stabilizing engine speed.